Yes.
Okay, cool. So we're going to formalise our naming of different parts of the wave and go through a couple of equations that we're going to use. And first of all, we're going to do it like this. And you can kind of think about this graph here as being like a photograph of a wave. Like it's a wave in motion, but it's frozen in time. Like time is not moving. And so as we move along the medium, like along the spring that the wave is travelling through, we can see that the wave goes up and down and up and down. So it doesn't matter if it's a transverse wave or a longitudinal wave, this is going to work for both. Thinking about, model it as though it's a transverse wave because we've got the displacement of the medium at right angles to the medium. So like, that's our displacement going up and down. The first important thing we have to name is that the amplitude of the wave means like the distance from the equilibrium position, like that x-axis, up to either the highest point, the crest, or the lowest point, the trough. And those are both the same. They're going to be the amplitude of the wave. The second thing that we're going to name is the wavelength. And the wavelength, the important thing with wavelength is that we always measure from one part of the wave into another identical point further on down the wave, one wavelength, like the next identical point down the wave. And so I'm going to go with the crest of the wave, because it's really easy to see, and go along until I find the next crest of a wave. And so that distance there is what we call the wavelength. And wavelength is measured in the same thing as normal length, it's measured in meters. And so wavelength,
1,000 centimeters.
symbol is lambda, Greek letter lambda, measured in meters. So that's the kind of information that we can get off a graph that's like frozen in time photograph of a wave. It could be a photograph of the sea, and as you look along the surface of the sea, it's got like cresty, trophy, and the distance between two crests or two troughs or two of any of the same point on the wave is equal to the wavelength. Instead of freezing the time, we're going to have a look at what would it look like if we froze our position and time was allowed to keep moving. In other words, what if you took your little boat out onto the sea and anchored it at a fixed position, and the waves went past you and your little boat went up and down and up and down. So you're not moving backwards or forwards, it's time that's passing. So still displacement in meters on the y-axis. On the x-axis, rather than being the position on the medium now, it's going to be the time, measured in seconds. And the interesting thing is that the graphs look absolutely identical. Like we can't tell from looking at the graph the difference between a photograph of the surface of the sea going along, or what we would experience if we anchored our little boat out at sea and it went up and down and up and down. It's exactly the same thing. And the amplitude of the motion is still the distance from the equilibrium position, like where the water would be if it was a flat day, up to the highest point or down to the lowest point, the crest and the trough. But we're going to need a different name for the distance from one crest to the next. It's not going to be a wavelength, because on our first graph we were measuring distance on the x-axis. This time we're measuring time on the x-axis. What's the time called from one? The time for one wave to go past the...
Sound of repeating?
Okay. It's the period of motion. Period, symbol capital T, in seconds. And the other things are going to be the same on this graph. The amplitude is going to be the same. Displacement, we can say all the same things about that. And that's what's useful, what we can drag out of this is an idea of frequency. So frequency is very closely related to time, like we were hearing before. The frequency is the number of cycles per second, like the number of times per second, whereas the period is how long it takes. And so we can link those two ideas together with F is 1 over T. So I'm going to box that one up in red because that's going to be on your resource sheet when you come to do your exam. So you don't need to remember it, but you are going to be expected to use it. And so frequency is measured in hertz. Why is that classic cartoon like the megahertz, gigahertz? You seen that cartoon in the corridor? Yeah. That's why it's fast. So period in seconds. So the word for hertz is like someone's name, H-E-R-T-Z, but we just write H-Z. But then hang on, we can look back at this and be like, the period is measured in seconds. And so what else could we measure frequency in other than hertz?
Cycles a second.
So cycles per second or just per second, like how many per second. So Hz, or more fundamentally, we would write S to the power of -1, which means per second. We're happy with that. So now we've got the last thing, the final thing, is we've actually got an equation which allows us to link together the wavelength of a wave and the frequency of a wave with the speed that that wave travels at. That looks like that, V equals F lambda. And so the F is still the frequency in hertz or per second. The lambda means wavelength measured in meters. And look, we've got meters per second, which is the unit for velocity. Like that. So we can use this equation to find any unknown from wavelength, frequency, and wave speed. And what's interesting, what's useful for this in terms of thinking about some of the concepts we've learnt already, is that the frequency of a wave stays constant when it's refracted. So what we know happens in refraction is that when a wave passes from less dense to a more dense medium, the speed goes from fast to slow. The frequency stays the same. Frequency always stays the same. And that means that the wavelength also drops from long to short. And it's that changing wavelength that actually causes the waves to bend. We'll have a look at that in more detail later. Are we good?